Spacetime interval. In our Newtonian world, we think space and time are independent of each other. We assume it makes sense to talk about distance without mentioning time, and that it makes sense to talk about durations of time without mentioning distance. On relativistic view, however, space and time are not independent entities. They are interconnected by a four-dimensional space-time. Space takes up 3 dimensions, and time is a 4th dimension. By the way, if you like this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. Let us imagine a person is on a train moving at a very high speed, say 0.6 c. This person begins a meal that was served on a 20 centimeter diameter plate, its proper length, at 7 o'clock and finishes at 7:15, according to a clock on the train. The two events, beginning and ending the meal, take place at the same point on the train. So the proper time between these two events is 15 minutes. Now consider the same events as viewed by an observer at rest on Earth. Let's calculate how long this meal takes, and let's also calculate the diameter of this plate. First of all, let's find the Lorentz factor, and then we use the formulas for length contraction and time dilation. The observer on Earth measures the eating time as 19 minutes. The plate is only 16 centimeters wide. Thus, to the observer on the Earth, it looks smaller but lasts longer. Clocks moving relative to an observer are measured to run more slowly as compared to clocks at rest. The length of an object moving relative to an observer is measured to be shorter along its direction of motion than when it's at rest. We have seen that the position and time of an event varies from one frame of reference to another. We can see that our notions of time intervals, the time between two events, and space intervals, the distance between two locations, varies from one frame of reference to another. In other words, absolute time and absolute space are not invariant, unchanging properties when moving from one inertial reference frame to another. In special relativity, a quantity is invariant when it remains unchanged under Lorentz transformation, and thus it has the same value in all inertial frames. An invariant quantity is useful because it gives different observers a quantity about which they can all agree. We have just seen how space and time are connected by the fact that time dilation must go hand in hand with length contraction. So this fact led some physicists to look for a quantity that could be invariant and that would relate time dilation and length contraction. This quantity is called space-time interval. The figure shows a simple light clock that consists of two mirrors facing each other across a room. An observer at rest watches light reflecting between the mirrors. The distance across the room is L. Now another observer at rest on Earth watches the light clock moving relative to the stationary light clock to the right, parallel to the mirrors, at constant velocity v relative to the mirrors, watching the reflections. So the light is following a longer path and thus will take a longer time. The interval between ticks is therefore not the same. However, the distance between the mirrors is the same. Applying Pythagoras' theorem to the yellow triangle, we get the following result. Now suppose the light clock is traveling faster than the previous one. So the distance traveled by the trolley and light is longer. Applying Pythagoras' theorem again gives the following result. We now can equate these equations, and after replacing v times delta t by delta x and simplifying, we obtain. We can see that the quantity c times t squared minus delta x squared is invariant. C times t has the dimensions of length, and this leads us to an invariant quantity known as the space-time interval. In relativity, space and time are intrinsically linked into a single concept called spacetime. The interval between two events across spacetime is invariant. Different inertial observers can measure different times between events and different distance between events, but they must all measure the same interval across spacetime. The space-time interval is denoted by delta S. The S stands for separation. It's about the separation between events. Let's see how the space-time interval works. To solve the item A, it's a good idea to illustrate the problem. We now calculate the value of the Lorentz factor. With the Lorentz factor, we can calculate the time and position measured in the second frame of reference. We use the Lorentz factor for x prime and for t prime. We can find the space-time interval in S and in S prime. We can see that the space-time interval between the two events is constant for all observers. Let's see how to solve this example. To solve the item B, first we calculate the time taken as seen from the laboratory's reference frame, and then we find the space-time interval. Although the laboratory's reference frame and the electron's reference frame disagree about distances and times, they do agree on the value of the space-time interval between the events of the electron passing the start and finish lines. This fact allows us to calculate how long an observer traveling in the electron's reference frame will record between the two events. Before continuing, let's return to the example of the light clock. The observer at rest in the room sees the light reflected between the mirrors. These two events, the light leaving from the bottom mirror and the light returning to the bottom mirror, occur at the same place. So the spatial distance the observer at rest measures between the events is zero. Now we can go back to solve the item B. In the electron's reference frame, the electron is stationary, and the start and finish lines move towards it with the start and finish events occurring at the electron. This means that for this observer in the electron's reference frame, the spatial distance between the events is zero. Delta x prime equals 0. We now perform the calculations. Pay attention in the next example. First, let's find the distance between Earth and extra according to John. John observes Maria traveling the distance of 24 light years. To solve the item B, the value of the space-time interval between the events of Maria passing Earth and Maria reaching extra is the same for John and Maria. So we use this fact to calculate how long Maria thinks the trip takes. Maria is present at both events. The spatial distance she measures between the events is zero. Although the spatial distance Maria measures between the events is zero, Maria sees Earth and extra passing her traveling at 0.8 times c and separated by 18 years. Thus, the distance is 14.4 light years.